Today's presentation features Dr. Marshall Wigwe. Dr. Wigwe is a reservoir engineer with a PhD in petroleum engineering from Texas Tech University. Please welcome Dr. Wigwe as he presents the cost of wrong decline curve analysis for strong water drive reservoirs. In today's oil and gas industry, accurate decline curve analysis is essential. Join us as we explore the implications and consequences of incorrect decline curve analysis, specifically for strong water drive reservoirs.
Hello everyone. Today I'm going to be talking about decline curve analysis for strong water drive reservoirs. My name is Marshall. I'm going to talk about myself some more in a few minutes. All right, so again, my name is Marshall. I'm a reservoir engineer here at PHDWin, TRC Consultants LC. So what do I do here? So I mostly run the training program for the company. So everything for PHDwin training, whether it's for version 2 or version 3, all the documentations for PHDwin, from the help file to internal documentation, pretty much most of the things you get to see in writing, I have to be involved one way or another. Being part of training and doing a lot of client facing during training, I get involved in QC as well. The training is part of the QC process. And then, of course, we spend some time to QC the new build. So always involved in developing and improving the program. I also get involved in support. Not surprisingly, most people that call me for support are people that have been part of the training, or sometimes I just get on the support email and help out with support here and there. So pretty much I get to do almost everything in the company. I have a master's and PhD in petroleum engineering from Texas Tech University, GUNSAP. I also have a bachelor's in chemical engineering from Rivers State University in Nigeria. I like to show this slide usually during training to pretty much let my audience know the other aspect of me that they don't tend to see often. So I like to volunteer a lot, whether it's with, during my time at Texas Tech, I volunteered a lot with American Rock Mechanic Association, SPEA, AADE, and a lot with SPE. Both the one at Texas Tech chapter and then the Permian Basin section. But since I graduated, I've really been involved with the SPE Gulf Coast section, and I got this award in 2022 for Exemplary Volunteer Award for my job leading the Community Service Committee as the chair. So one of the notable, some of the notable projects we did, we have the bed building project. So this was a project we did in partnership with Sleep in Heavenly Places. That's an organization in Houston. Well, I think they have chapters all over the place. But we partner with the chapter in Houston to build around 40 beds for kids that are still sleeping on the floor. It's going to surprise you that Houston is still recovering from the impact of Hurricane Harvey. So, but we get to do that project. Thanks to a lot of the volunteers, the young professionals from SPE Gulf Coast section and other people, we were able to build about 40 beds that we distributed to these kids, and you could see the smiles on their face when they were receiving this bed. So that's a great project we did. We also got involved with a career talk with Spring ISD in Houston. We talked about the oil and gas industry. We talked about STEM in general, and pretty much provided guidance to them on what it takes to be part of the oil and gas industry, to have a career in this booming industry. So it's going to surprise you. A lot of people don't have role models like us. If you're listening, probably a professional, you have a degree, you went to college, you even have an advanced degree like myself. So our kids, they get to listen to us, they get to see role models around them. A lot of these kids don't get to see that kind of role model, So this kind of provided us an opportunity to interact with these kids, let them know about the industry and encourage them to pursue a career. Maybe if they decide to pursue a career, they remember this conversation and they join the oil and gas industry. But regardless of what they pursue, the satisfaction is that we are hoping that this conversation is going to, plant a seed inside of them to think beyond high school. In college, think about getting a better career for themselves in the future. We also got involved with teachers in STEM. So we took a lot of the teachers in Houston ISD to OTC. This is something SPE Gulf Coast section does every year. We take them to OTC, we take them through a tour of the exhibit halls. They get to talk to some of the exhibitors, get to understand what they do for their companies. And hopefully, I think the hope is that they'll be able to carry that message to the classrooms, with that excitement, something they've seen firsthand, talk to their students about the oil and gas industry, what we do, and that is going to probably leave a positive impact upon their lives. So I was given an award for that. Now on the picture, that's me right here. That's the award. You'll probably be able to see it behind me on the screen. And that's my beautiful wife, Betty. She's an accountant. Next is Sebastian. Sebastian is a marketing guy here in PHDWin. So he does a lot of the marketing job, great job. If you receive an email from us, it's probably coming from Sebastian. Next to Sebastian is Raymond. Raymond is a friend of mine, went to tech together, did both masters and PhD. He currently works with EGA Solution in Houston as a multi-phase flow analyst. Next is Allison. Allison was with us here last year, and she was part of the sales team. Incredible person. Next is David. Dave is the president and founder of TRC Consultants, and he is a great mentor to me, and he's always not too far from me. Can go to his office, ask him question, anytime I want. He has a lot of experience, showing great leadership for PHDwin. Finally, I have Ifa. Ifa is also one of our sales guy. He does a lot of international and local sales and demo walkthrough, so he's a great guy. So Ifa and Dave currently are in China at the time of this presentation, and they will most likely be doing this similar presentation to a conference there in China. Now you can see Ifa is Texas Tech Marshall, Texas Tech Betty, my wife, Texas Tech Raymond. So Texas Tech seems to be dominating this presentation. But anyways, that's shout out to my alma mater. So a little bit about TRC. TRC Consultants has been in the petroleum engineering business since 1986. In 1995, TRC was incorporated as a limited liability corporation in the state of Texas with the name TRC Consultants LC. During 1986, TRC was primarily a contract petroleum engineering firm specializing in reserve evaluations. Specifically, TRC developed bank reserve reports and consulted on oil and gas property acquisitions. To facilitate our work, TRC developed in-house engineering software that integrates the client curve analysis, economics, and database management. This is what we come to know as PHDwin, the software. Although TRC originated to perform contract reserve evaluations, petroleum engineering software development, sales, and support has become our main business focus. Many of the features we have developed in PHDwin are the result of our own engineering needs, as well as recommendations from our many users. All right, so this is what we're going to be covering today, kind of the outline for the presentation. I'm going to have a quick conversation about production forecasting. Then I'm going to go deep into apps. In the apps decline model, I'm going to review some of the projection history, review potential theoretical support for apps empirical technique. Then using the conventional apps technique, I'm going to evaluate a project that has 5 wells that are high water cut wells, then I'm going to use Arps, then create a cash flow for those 5 wells. Next, I'm going to review techniques for projecting mature water floods. We're going to be reviewing the water oil ratio versus Cum Oil projection technique. We're going to compare theoretical basis of this technique with that of Arps. Using water oil ratio versus the Cum projection technique, we're also going to project those 5 wells and create cash flow. Then we'll go ahead and compare the results of both techniques, make recommendations on not really what is the appropriate technique, is pretty much on how to provide the engineer a guide on the right way to pick what technique for the specific situation. Then we'll go through the conclusion. All right, so let's get started. Production forecasting. So in the oil and gas industry, this is the prediction of future production rates of produced fluid. So we're talking about oil, gas, water, and if you have other products, you also make forecasts for those. It is used to estimate the ultimate recoverable volume, which is the EUR of an existing well, like we have for well A right here, or a new production entity. So this entity could be a well, it could be a lease, it could be a reservoir, or even a field. So in the top graph, we have an existing well with historical production data, and we've gone ahead to put a projection on the recent data into the future. The figure on the bottom, the graph, is pretty much an undeveloped well that we had to create a type curve for, and then we projected the potential, the future EUR for this undeveloped asset. So production forecasting, whether it's an existing well or a brand new well, we can actually have a forecast for those 2 situations. All right, so in this slide, I'm going to make a few comments about the task, the exercise, what we do when we do production forecasting. Production forecasting should not be construed as merely an exercise in curve fitting. This is because there are several reserve estimation methods used in the industry that the engineer can select from. So we have the analogy, we have decline curve analysis. The engineer can also select volumetrics, material balance, rate transient analysis, or reservoir simulation. Now, from this plot, I got this from Dwayne's presentation. You can see that decline curve analysis is the most frequently used method for production forecasting. So this is the same statement. Decline curve analysis is the most used technique for estimating reserve. Now, there are different decline curve analysis methods. Each have a specific application depending on the reservoir type and the drive mechanism. So the reservoir type, whether it's an unconventional reservoir, conventional reservoir, drive mechanisms, we are talking about water drive, solution gas drive, and other types of drive mechanisms. So this is a table that was generated from a presentation by a 2015 presentation by Dr. John Lee and Dr. Blassingame. I think in the 2015 period, SPE had a series of webinars that they had to talk about different topics. One of them was production forecasting. So as we can see, these are some of the production forecasting that are being used in the oil and gas industry when we talk about decline curve analysis. The first is Arps decline model, which Arps talked about sometime in 1945 in its paper. Then we look at the stretch exponential decline model, the power law exponential and the extended version, Duong and modified Duong decline models, linear, transient hyperbolic, and then the extended exponential decline model. Now, from the source of this data, you can see that most of this decline model, with the exception of Arps, they all came on board from 2008. And this is pretty much around the time that we started, exploring, not really exploring, developing unconventional resources. So essentially, they were tailored towards being able to predict that early time transient period for unconventional reservoirs. So as you can see, they are all good decline model types if you want to predict those early time behavior once you put an unconventional well into production. Now, the Arps on its own, it was designed for the late and the boundary dominated flow based on the assumptions inherent in the development of the Arps decline model. However, even if Arps originally has a B factor, which is a really important parameter in Arps decline model. So originally, we see that the B factor can go from anywhere 0 to 1. All right, so even the Arps have been extended such that you can have a higher B factor to capture that early transient period. So the Arps itself, it can be modified to, be able to perform really nice in that early or transient time period. But essentially, these are all the decline models that are in existence in the industry currently. And the engineer has to make a selection from this decline model depending on the type of reservoir, depending on the drive mechanisms. So overall, the engineer, a good production forecasting needs, I wouldn't say just these three things, but these are really important in my opinion. So they're going to need the engineer. So this is someone who has the educational qualification or has obtained appropriate training and can make good engineering judgment based on that training or even from experience. So the engineer has to also have to have a good understanding of applicable engineering principles in order to be able to screen these techniques for use in specific applications. Hence, even with a good auto fit in programs like PHDWin, this good auto fit wouldn't be a good replacement for the engineer within any organization. So we still need the engineer to be able to apply his knowledge to make selection rather than just blindly auto fitting every single case without thinking about the engineering aspect of it. Okay. So in this section, I'm going to be talking about the Arps, the birth of the Arps decline curve analysis, do some historical review. So the Arps model really started with J.J. Arps' 1945 paper where he proposed an empirical prediction technique for use in production forecasting. In 1956, Arps offered a further refinement to his technique. In 1963, Browns demonstrated a diffusivity equation-based theoretical model for J.J. Arps' original work. Now, between 1980 and 1983, Fedkovich came up with refinement of the diffusivity equation based theoretical basis by developing type curves. And those type curves have been really, really popular in the industry since they were developed. Between 1993 and 1995, Dr. Blasingame and his colleagues, they presented two papers that talked about extended Fedkovich type curve, extending that to variable rate and pressure for liquid and gas declines. So they presented modified Fedkovich type curves and developed additional type curves for injection wells, where they integrated pressure transient and other water flood surveillance data. So the diffusivity equation is one of the bases upon which we make some of these predictions. And the diffusivity equation is derived essentially from three important concepts. The first is going to be the continuity equation, which is pretty much a statement of the conservation of mass. So which says mass in minus mass out is going to be accumulation, right? The other one is going to be the Darcy's law, which relates pressure gradient to the flow rate. And finally, a non-compressible or slightly compressible equation of state, which pretty much states that volume is independent of pressure in this specific situation. For Arps equation, Arps projections theoretical validation requires that certain simplifying assumptions be applied to the diffusivity equation. So the condition under which the Arps equation have the most validation are under steady state and pseudo-steady state reservoir flow conditions. And generally, these are known as the boundary dominated flow. The idealized flow conditions for steady state flow, this is defined as a condition where the absolute pressure profile of a flowing reservoir stays constant with time. So we don't see pressure changing with time. So, and this is really, really important for primary recovery with edge water drive, or even in secondary recovery, whenever you're talking about water flood, that's a good application for that. But it's an idealized condition, flow condition. Pseudo-steady state flow condition, on the other hand, is defined as a reservoir condition where the relative shape of the reservoir profile remains constant over time. So absolute pressure at different points can be changing, but there's the delta P, the change in pressure is going to stay pretty much constant. The Darcy portion of the diffusivity equation defines pressure profile within the reservoir. And then for this pressure profile to be in steady state or pseudo-steady state, the parameters of the Darcy's equation need to be constant over time, so they shouldn't be changing. So permeability, viscosity, the flow area, the length of the flow path, these are they pretty much need to be constant over time for steady state and pseudo steady state. Now, in a strong water drive reservoir and water flood, all these factors are changing with time. You know, the changes may be slow or may be insignificant in a mature water flood or in a high water cut well. If this is the case, then we can probably still apply a steady state and pseudo steady state assumption for Arps decline model. So what does a typical water cut profile look like? So in a water drive or even in a water flooding operation, as production continues, you see that the waterfront is going to move closer and is going to encroach the reservoir. And eventually, we're going to have a water breakthrough and water cut is going to increase. So IHS did this report in 2016 when they were still IHS Energy on water cut profile. And I think this was done for Permian Basin. So we can see that high water cut well in that paper, they define as well with water cuts around 80% or greater. And this translates to a water oil ratio of 4. So Arps projections are regularly used for high water cut wells. You know, the question becomes, is it the right tool for a high water cut well? And that's pretty much what we're going to discuss in this presentation. So let's do some testing and apply this technique to some high water cut wells. So we're going to be applying decline curve analysis to some wells that we have. So the first well is going to be, it's a high water well. This is a Hensler 121 well that's been producing from the Red River Reservoir since 1984. So it's producing from the Comertown South field, and this is in Sheridan County, Montana. So we see an economic EUR value here showing 523,000 barrels. So actually this is the historical, this will be equivalent to the historical production since we haven't put a forecast to this well. So far the well has made over 500,000 barrels of oil. Now, if you look at this well, we have water, oil, and total fluid on the left axis, and the water oil ratio on the right axis. So what we see for the water oil ratio is this has been trending up over time, but over the last 5 to 10 years, you see that the water oil ratio has been hovering around 9, which translates to a water cut of about 90%. The second case is the Jones Quam 1 well. This is also in the Sheridan County in Montana. And cum production for this well is a little bit over 200,000 barrels. And similarly, we see a trending water oil ratio, but for the past 5 to 10 years, it's been probably around 30, 10, 20, 30. That's around 97% water cut. The third case is the Osaka 1 well, also in the Goose Lake field in Sheridan County, Montana. This has produced so far 167,000 barrels of oil since 1985. Again, we see that trending upward trend for the water oil ratio, but somewhere over the last 5 years, it's been probably around 40, which is 98% water cut. The fourth well is the Couchney 1 well in the Vought field in Roosevelt County, Montana. For this particular well, it's produced over 1.5 billion barrels of oil. So that's a really prolific well. And for this well, you see water flood, the water oil ratio has some behavior that is going up and down. But since 2000s, you see it's been trending up. And currently we see the water oil ratio also around 40, which is also like a water cut of 90, 97.5, 98. So finally, the last case is the Trimble well number 2, also in the Vought field in Roosevelt County, Montana. This has produced about 500 million barrels of oil over the life since 1972. Again, over the last 20 something years, we see a trending up of the water cut up to when the well was probably shut in around 2019. And for this particular well, before it was shut in, we see that water oil ratio is around 80, which is around 99% water cut. So what we're going to do is to use the Arps decline model to evaluate these 5 cases. We show the results and we run a cash flow using some 2022 year-end price forecast that we have. So we're going to use the same price forecast, the same expenses for each case when we evaluate this. So what we did for Hensler well number 1 and for all the cases, we came here, we applied Arps decline model to forecast the oil production. Then we also put a forecast on the water production. With both forecasts, we can see that the water oil ratio, is still trending up. We calculate the water oil ratio and then the total fluid values. So right now we see that the economic EUR has gone up, and then that's the value for the asset. So this is a plot of the log of the water-oil ratio as a function of the cumulative oil production. We see that using the Arps decline, we don't see a straight line on this curve. You see that the forecast of oil and water production shows the water-oil ratio is pretty much a curve on this plot. We're going to talk about this pretty soon. Okay. And this is the cash flow using the assumptions for prices and expenses on this case. So we see that the remaining reserve for this well is around 41,000 barrels of oil. And then the net present value at a discount rate of 10% shows $740,000. So we did the same thing for the other 5 wells. The Jones Kwan well, again, we put a forecast on the oil production, historical oil production, and we also put a forecast for water production. Similarly, we see the performance of the water-oil ratio on the log water-oil ratio, Cum oil production. Again, it's curving upwards. And this is the cash flow. So for this case, we are seeing a remaining reserve of 46,000 barrels of oil and around $736,000 in discounted cash flow. For Osaka 1 well, we see similar result. For this case, we see around 6,000 barrels of oil remaining, and then 35,000 in net present value at a discount rate of 10%. For the Kochny 1 well, the remaining reserve, we're seeing 185,000 barrels of oil and $4.2 billion in net present value. And finally, for the Trimble number 2 well, we did something similar, and the remaining reserve for this is 33,000 barrels and $402 or $403,000 in net present value. So Arps implicitly is, whether it's directly or indirectly, in most Arps modeling solution, the assumption that has been made is there's a depleting reservoir energy, right? And then there's a homogeneous reservoir fluid and rock properties across the board. So those were some of the implicit assumptions in deriving the Arps or in the Arps original model. However, for strong water flood, for a water flood or a strong water drive reservoir, these are not good candidates for Arps. And these are some of the reasons why we are making this statement. And these have been backed up in the literature. A lot of researches have been done. And this is pretty much in line with the research that's been done in the literature. So a strong water drive reservoir have consistent reservoir energy over the life of the well. So reservoir energy is not depleting, and then this reservoir is exhibiting infinite acting flow condition. So as the oil is being produced, you see water encroaching towards the well. So there's a constant support from an external energy. Even for water flood reservoir, it also has consistent energy supply after fill up and during pressure maintenance injection. Again, reservoir energy is not depleting, and this is going to be exhibiting infinite acting flow condition. In addition, relative oil and water permeability are dependent on the changing oil and water saturation. And these are changing for these two situations, right? Things are not constant. So the controlling factor after breakthrough is going to be the mobility ratio. And then the relative permeability changes over time as a function of saturation. And you can see this changes. The relative permeability curve is changing with time and then as a function of saturation on the x-axis. Let's quickly talk about water flooding. So during the same period that Arps was doing his work, multiple other engineers were developing sophisticated water flood prediction models. And this work culminated in the 1971 SPE Dallas monograph, The Reservoir Engineering Aspects of Water Flooding. So as an alternate method, we see that the reservoir, whether we're looking at the reservoir engineering aspects of water flood in the Dallas monograph, water flooding being taught by William Cobb for the William M. Cobb and Associates Company. Oil and gas properties evaluation, there are a lot of alternative methods discussed there. So for this alternative method we're about to discuss, whether we're also looking at the analysis and interpretation of water-oil ratio performance. This was a paper presented by Dr. Blassingame. Then we also see a work done in the decline curve analysis models based fluid flow mechanics by Roland Horn. Now, these papers demonstrate a common technique for projecting oil and water volume as a function of time after fill-up and breakthrough. So this method we're talking about is the water-oil ratio versus cum oil plot. So how do we go about this methodology? We have historical water-oil ratio being plotted against the cumulative oil production. So we have water-oil ratio on the y-axis on a log scale. Then oil produced is plotted on a linear axis on the x-axis. So this plot is commonly referred to as a water-oil ratio versus cum oil plot or water-oil ratio versus NP plot. When values of water-oil ratio exceed 1 or greater, we see that the log of water-oil ratio versus cum oil may become a straight line, and as a result, you can go ahead and project that straight line. If the total fluid produced is then projected as well, we can combine the water-oil ratio with the total fluid to iterate and calculate the water and oil volumes each month into the future. So with the future oil and water volumes projected by month, we can run cash flow and calculate the economic limit for each of these cases. So this is what it's going to look like. We're going to put a projection for the total fluid as a function of time. We're going to project the water-oil ratio using the log of water-oil ratio versus cum oil plot. We'll put a straight line through that data. Then using these two data, we're going to go ahead and iterate and calculate both oil and water production. So we're going to apply the log water-oil ratio versus cum oil plot methodology to the same 5 cases we discussed earlier with the Arps decline model. So remember, at the end of the day, we're thinking about, in a high water drive reservoir, a high water cut reservoir, which is the appropriate method? Should we just go ahead and apply Arps decline model, or should we consider other methodology? Which one is the appropriate thing to do? So in this case, we go ahead for the Hensler 121 well. We put a straight line projection, so we pretty much can see the straight line trending on the log water-oil ratio versus cum oil plot. Water-oil ratio is increasing, so we see that straight line. We go ahead and project that straight line, usually up to a limiting rate of water-oil ratio. We can get up to 100 if we want, but usually anywhere from 100 to 200, which would translate to greater than 90% water cut. So on the log water oil ratio Cum Oil plot, we only project water oil ratio curve. Then on the rate time semi-log rate time plot, we go ahead and also put a projection on the total fluid. So with the two projections, we see that we have enough information to be able to calculate both the water production and the oil production. Now, using that data, we run cash flow for the Hessler well number 121. So for this situation, we see a remaining reserve of 81,000 barrels of oil and the net cash flow of $983,000 at 10% discount rate. So we do something similar for the Jones-Quam well. Again, we see that straight line. We put a projection to that straight line. We also put a projection to the total fluid data. Then we iterate both oil and water production. So for this, for the Jones-Quam well, we see a remaining reserve of 57 or 58,000 barrels of oil and a discounted cash flow of $750,000. So we do something similar for the Osaka 1 well. And we see the remaining reserve of 12,000 barrels of oil and a $76,000 in net present value. Same thing for the Cochin Roosevelt well. So I keep emphasizing the fact that we can see this straight line on the water oil ratio versus Cum plot. And for the Cochin 1 well, we see a remaining reserve of 290,000 barrels of oil and a $4.6 billion in net present value at a discount rate of 10%. And finally, for the Trimble 2 well, we do something similar. Remember, on a log, semi-log plot of water oil ratio and Cum oil, then semi-log of rate time plot, we see a remaining reserve of around 40,000 barrels of oil and almost $500,000 in net present value. So we're going to go ahead and compare the results of using Arps decline model and the water oil ratio versus Cum oil plot. So if we overlay both plots, you see the differences in projection. You can see that on the curve. Now we see the difference between the water oil ratio and Arps projection. So for the water oil ratio for the Hessler 121 well, we see 81,000 barrels in oil production forecast, remaining reserve, and 41,000 for the Arps projection. And this is almost a 40,000 barrel difference in remaining reserve. So that shows that the water oil ratio methodology is showing a 95% increase in reserve, a 78% increase in non-discounted cash flow, and a 32% increase in the discounted cash flow. Similarly, for the Jones-Quam well number 1, we see a difference in 25% for the oil reserve. We see an increase of 12.5% in non-discounted cash flow and a 1.38% increase in the discounted cash flow between the two methods. For the Osaka case, again, we see a 95% increase in oil reserve, 136% increase in non-discounted cash flow, and 113% increase in discounted cash flow. So similarly for the Cochney well and for the Timber well, we see our performance of the water oil ratio methodology over the Arps methodology, right? So fundamentally, it's not about overperforming or underperforming. As engineers, we are pretty much thinking about the theoretical basis, right? Is this the right method for this application? So these are high water cut wells. They have some external energy support. Am I using the right technique? Am I using the right method? So rather than just use the Arps decline model to put across all cases, we need to think about some of this. We need to think about what's going on in the reservoir. We need to think about the method, the theoretical basis for this methodology, which one is appropriate. And these are some of the things that an auto fit wouldn't be able to detect. You can put an auto fit on anything pretty much. It's going to use that data to auto fit it. But is that the right method, right? So we've seen that standard Arps and water oil ratio projection methods, they are both empirical, right? And they both have similar theoretical basis, but the projection based on water oil ratio versus NP incorporates the fractional flow theory better than the Arps. Arps doesn't even take that into account. So Arps projection may be used in strong water drive reservoir, but that should include a small hyperbolic exponent. So there are B factor recommendation in literature depending on the drive mechanisms, how you can use that, right? So you have to use the appropriate one for the specified drive mechanism. So use of an exponential decline is going to essentially under-project your ultimate recovery, as we have seen in this analysis. Only data with relatively consistent reservoir properties should be used to project from for the standard Arps. And the data to be used to project from may not be readily identifiable. So you have to look at the plot, you have to look at it and say, okay, which portion of the data. So rather than using every data, you look at a portion of the data that is consistent to be able to make that projection. The necessary hyperbolic exponent, so even if you're going to use a B factor, the one you're going to use may not be readily identifiable from the plot. So you really have to do an additional work as the engineer to be able to make the right decision. So here are some of the concluding remarks for the water oil ratio versus cum oil plot. So this method is going to require a straight line to appear on the log of water oil ratio versus cum plot. So that straight line is really, really important. So the appearance of that straight line pretty much, shows you what data portion that you're going to be using for that analysis, right? So now multiple straight lines may appear over the life of the well due to operational consideration, but you're most likely wanting to be using the last set of straight line that appears. So I'm not going to use a straight line that appears years and years ago. I'm going to look at the most recent data and use the most recent straight line to make that projection into the future. If no straight line appears and water oil ratio is greater than 5, then we should be really looking at operational changes. Something is causing the change that we're looking at. So, and this is really, really important. So these are some of our recommendations if you're going to be evaluating a high water cut well. So remember, this could be a just strong water drive reservoir or maybe for water flooding operation. So always create a log water oil ratio versus NP plot to identify what data to project. Then use the log of water oil ratio versus NP, the linear portion with a total fluid time-based projection to iterate the oil and water volumes over time. If you plan to create an Arps projection, use the log of water oil ratio versus NP to identify the correct hyperbolic exponent to use. So you can quickly look at that data and you see the period that could give you the right data. Once you fit the projection for that period, that should be able to give you some guidance on what the B factor should be, right? So this may be required for infield drilling projects where no historical data is available, and an Arps equation can be better manipulated for that purpose. Now, the analysis is best done on the most granular basis. So here we're talking about at the individual well level, you know. So even if you have like a pattern in a field, maybe a 5-pattern water flood, and you may be tempted to combine all 5 wells, you know, the 4 producers and the injector, then do the forecast for those patterns. So we still recommend you do for the individual wells. So even in those patterns or looking at the entire reservoir level, we still recommend you do this evaluation at the well level. You know, so the well level log water oil ratio versus NP should be performed to identify wells appropriate to combine. If log of water oil ratio versus NP projection are considered too aggressive for proved reserve category, then those projections should be considered for proved for plus probable. So you can bump that into the 2P reserve category. All right, so that pretty much brings to an end this presentation. Thank you for your time, and I'm hoping that you've learned something really important in this presentation. And primarily that has to do with you need to look at the data, you need to understand the reservoir, and you need to be able to make the right decision based on sound engineering judgment. So again, thank you for your time. This is the contact for our sales team, for our training team, and then for our support team. I really encourage people to get training on how to use PHDwin to do this type of evaluations if you don't know how to do that already. Support team is always here 24/7 if you have quick question on how to quickly do some of the setups. And if you don't have PHDwin, please contact our sales team. They'll be able to guide you on how to pretty much get set up. So thank you very much. Yeah, hope you enjoy the rest of your PHDwin week.
Thank you to Dr. Marshall Wigwe for that technical and informative presentation. We want to thank everyone who has tuned into PHDwin Week so far.